system of differential equation in which the coefficient matrix A has distinct and real and distinct roots. Okay, the case one was when the roots are real and distinct. For example, let's have a revision to this, maybe with the help of an example. For example, if we have a system which is basically nothing but dx by dt is equal to a up completely, there may be a minus 4 1 1 1 5 minus 1 0 1 minus 3. Now the system is 3 by 3 and the vector is x, y, and z, unknown vector, where x vector is what? It is. We need to solve this system of first order differential equation where the coefficient matrix is this. In order to solve this system, what we do, we need to find the eigenvalues of eigenvalues and eigenvectors of this coefficient matrix A. So the matrix A is this one, negative 4, 1, 1, 1, minus 5, minus 1, 0, 1, minus 3. So how do we find the eigenvalues and eigenvectors? In order to find the eigenvalues, we write characteristic equation. Characteristic equation is what? It is determinant of A minus lambda I equal to 0, or you can write determinant of lambda I minus A. It doesn't change anything, okay? Both are correct. Now we put the value of A and I, and we get it is determinant of A minus 4 minus lambda 1 1 1 and 5 minus lambda minus 1 and 0 1 minus 3 minus lambda, determinant equal to 0. Now I hope you remember how to simplify determinant in linear algebra using row and column operations. We can use elementary row operations and column operations in order to simplify this matrix. Otherwise, we have to expand this matrix by first column or by first row. So the simplest one is if we expand this determinant with respect to the column, this first column. Okay. Because there is a 0 entry here, okay, and we have only 2 cofactors. The third cofactor will automatically be 0. I hope you remember you did these things in linear algebra, math 120. If you have any confusion, you can ask me. Now we can expand this thing minus 4 minus lambda. Okay. The first is minus 1 to the power 1 plus 1. It is the first entry, the first row, first column. So minus 1 raised power minus 1 plus 1 times the cofactor of this this element is this determinant, which is 2 by 2, minus 1 1 minus 3 minus lambda. Now plus, now with respect to this element, second element of the first column, it is 1 times minus 1 raised power second row first column. So it is second row first column plus the cofactor of with respect to this entry. And how do we write it? We leave this row and this column and we write the rest of the elements in the cofactor. 1 1 1 negative 3 minus lambda. Okay. So this will be the cofactor, and the third entry is 0. So the third factor will automatically be 0, and we put it equal to 0. Let me add the people. So now after you can solve this 2 by 2 matrix, and after simplifying you will get definitely a cubic polynomial, and after solving that cubic polynomial for finding the roots, we finally obtain lambda 1 is equal to -3, lambda 2 is equal to -4, and lambda 3 is equal to 5. So these are the roots which we obtain after solving that cubic polynomial. How to solve that cubic polynomial? How to find its roots? I hope you know the polynomial remainder theorem. And if you don't know, you can read this in my lecture slides, which I have uploaded on lecture slide 13 of eigenvalues and eigenvectors. Slide's title is Eigenvalues and Eigenvectors. And on slide 13, I have explained this, how to find the roots of cubic polynomial. Now, once we have the roots, which are real and distinct, lambda 1 is -3, lambda 2 is -4, and lambda 3 is 5. Now, corresponding to each lambda, we have to find the corresponding eigenvector. When lambda 1 is -3, we assume that the eigenvector corresponding to lambda 1 is k1. Then, how do we find the eigenvectors? I told you in the previous lecture. We use this equation, a minus lambda I times k1 vector is equal to 0 vector. Now, we know the a, we insert lambda 1 here. K1 is unknown. We can say that this is K1, K2, and K3. Now, inserting all these values will get a homogeneous linear system. After solving that system, we can obtain the value of K, which is we obtain in this case. I hope you can do it and find the K1. So K1 is 101, and corresponding to lambda 2, which is -4, we obtain K2, which is, I hope you can find it. I have explained you how to find these vectors in the previous lecture. It is 10 minus 1, and corresponding to lambda 3, we obtain K3, which is 181. So we don't need these constants, these parameters here. We can, if we obtain 3 eigenvectors corresponding to 3 eigenvalues, which are real and distinct, so we can write the general solution in this way. C1, K1, e to the power lambda 1, it is -3t, plus C2, K2, e to the power -4t, plus C3, e to the power 5t. So this is your general solution. I hope you get it now by inserting K1, value of K1, K2, K3 here, you get the solution. If the initial conditions are given, we can find these constants, constant of integration, C1, C2, and C3. I hope you get it. If you have any problem, you can discuss it. Now, the second case when the roots are repeated. Roots are real and repeated. And as an example of this question, let me take this example. That y dash z dash is 0, 0, -2, 1, 2, 1, 1, 0, 3 times x, y, z. It's a 3x3 system. And after finding its eigenvalues, first what we do, we have to find eigenvalues. After finding eigenvalues of this thing, you would see that we obtain lambda 1 is equal to 1 and lambda 2 is equal to 2 and lambda 3 is again 2. So this eigenvalue is repeated. Okay, it appears 2 times, the same root. Now one root is distinct and the other 2 roots are identical. In this case, we find the corresponding eigenvector here, corresponding to lambda 1, which is 1. We will definitely obtain an eigenvector because it is real and distinct. So we'll have an eigenvector corresponding to lambda 1. Now the question here is whether we obtain, there are 2 cases I told you in the previous lecture. There are 2 cases. Lambda 2 is true and lambda 3 is 2 again, repeated. Now the question is whether we obtain, then there are 2 cases corresponding to this. First and this, case 1 and case 2. The case 1 is we obtain 2 eigenvectors corresponding to lambda 2 is equal to lambda 3. Okay. This is the first case. That is we obtain K2 and another eigenvector K3. This is the first case. If first case is true, that for a single value, we obtain 2 eigenvectors. It is possible. Okay. If a homogeneous system involves, it has 2 independent variables, then we can have 2 eigenvectors corresponding to 1 eigenvalue. Okay. This is the first case. Let's do an example of the first case, and then we'll discuss an example of the case 2, and then we'll discuss the case 2 as well. Let's come to this board now. The case 1 example of case 1. Example which I had written there, that was an example of case 1 in which we obtain lambda 1 is equal to 1 and lambda 2 is equal to lambda 2 and 3 is equal to 2. We consider the same example. In that case, for lambda 1 is equal to 1, we obtain K1, which is, I hope you know how to find these eigenvectors. K1 is -1, 0, 1. Okay. Now, for lambda 2 is equal to, or lambda 2 is equal to lambda 3 is equal to 2. If we put this lambda and the corresponding a into the equation, which is a minus lambda I times some, you can say some y vector. Okay. You assume that this y vector is the eigenvector corresponding to this eigenvalue, okay, equal to 0. Now, if we insert that matrix minus lambda, we obtain 0 minus lambda, okay, 0 minus 2, 1, 2 minus lambda, and 1, and 1, 0, 3 minus lambda, times, you can say y1, y2, y3 is equal to 0, 0, 0. Now, what is the value of lambda? It is 2. We have to insert 2 here. And what do we obtain here? it is -2, 0, -2, and then 1, 2 minus 2 is 0, 1, and 1, 0, 3 minus 2 is 1. Okay, times y1, y2, y3. This equal to 0, 0, 0. Now this is a homogeneous linear system. And augmented matrix is what? Okay. Augmented matrix is -2, 0, -2, and 0. This 1, 0, 1, 1, 0, 1, 0, 0. So this is your augmented matrix. You can see that all three rows are identical. If we take -2 common from the first row, or we divide first row by -2, all the three rows will be identical. Okay. You can operate the -1/2 R1, one operation. The second, R2 minus R1, and then R3 minus R1. If you apply these three operations, what you'll get 1, 0, 1, 0, 0, 0, 0, 0, and again 0, 0, 0. So this is in echelon form, or you can say this is in reduced echelon form. Now we can write back the linear system from this augmented matrix in order to solve this system. Now, if we write back the linear system, what would we obtain? We obtain y1 plus y3 is equal to 0. This is all what we have got from that linear system. Now, you can see that there's no y2. So y2 and y3, we assume that y2 and y3 are free variables. Y2 and y3 are free variables. We can write y2 is equal to some s, where s belongs to r, and y3 is some r, where r belongs to r, set of real numbers. Now we can write the y1 is what from y1. Y1 is negative y3, which is negative r, it means. Now, if we want to write the solution y1, y2, y3, it is what? It is nothing but y1 is negative r, y2 is s, and y3 is r. Now, taking common the free variables here, how do we write here? We can take r common, -1, 0, 1, plus we can take s common, 0, 1, 0. So this is the solution. Is there any question from someone? No? Okay. Now you can see that we obtain two vectors, eigenvectors. You can call this one K2 vector and this one K3 vector. Okay. So corresponding to, what do we have here now? Corresponding to lambda 2 and 3, lambda 2 is equal to what? 2 is equal to lambda 3. So the roots were repeated 2 times, but we obtain two eigenvectors corresponding to a single eigenvalue, which is repeated 2 times. Okay. So we can write the two solutions corresponding to these two eigenvectors, and hence the general solution can be written in the similar way as we write in the usual case for the real and distinct eigenvalues. So thus the general solution is what? It is nothing but C1 K1 e raised power 1t plus C2 K2 e raised power lambda 2 is 2t plus C3 K3 e raised power again 2t. This 2 and this 2, they are same, but eigenvectors are different. So this will be the general solution. By inserting the value of k1, k2, k3, you get the general solution in this case when the eigenvalues are real and repeated. In the case 1, for each repeated eigenvalue, we can obtain a distinct eigenvector. Okay. In that case, we'll write the general solution in a similar way as we write for the real and distinct case, real and distinct roots. I hope you get it. If you have any question, you can ask me. Otherwise, we are going to discuss the next case. Now, come back to the previous, this one. We discussed that when the eigenvalues are repeated, but we can obtain eigenvectors equal to the number of repetition of that root. ठीक है, अगर ये 2 दफा रिपीट हो रही है तो हमें 2 eigenvectors मिल रहे हैं. अगर ये 3 दफा रिपीट हो रही है, we are getting 3 different eigenvectors. ठीक है. Now, this repetition of eigenvalues is called algebraic multiplicity. Algebraic multiplicity. Okay. Algebraic multiplicity of this root is what? It means how many times it is being repeated. So it is 2 times repeated. So algebraic multiplicity of this eigenvalue 2 is 2 because it is repeating 2 times. Okay. Whereas these eigenvectors corresponding to a root which has algebraic multiplicity 2, okay, then this is called geometric multiplicity. I hope you know this is these things you linear algebra course, algebraic multiplicity of eigenvalues and geometric multiplicity of the eigenvalues and eigenvectors. So this is geometric multiplicity. Geometric multiplicity of these eigenvectors is what? It is basically 2. यहाँ पे क्यों? क्योंकि एक आइगन वैल्यू के लिए 2 आइगन वेक्टर्स आ रही हैं. Now we are going towards the case 2. The case 2 is what? When we have eigenvalues which are repeated, whose algebraic multiplicity is greater than 1, but the algebraic multiplicity, sorry, geometric multiplicity here means we obtain only one eigenvector corresponding to lambda 2, which is repeated 2 times. Its geometric multiplicity is 1 when this is the case. Now let's do this with the help of an example as well. This one, yes. Let me change the board. The case 2 example. We need to solve this first order system of differential equation. 5 minus 4, 0, 1, 0, 2, 0, 2, 5 times x, y, and z. Okay. Now, I'm going to write directly the eigenvalues corresponding to this root, this system. So eigenvalues, I hope you can find now the eigenvalues easily. Eigenvalues are lambda 1 is equal to 0, and lambda 2 is equal to lambda 3 is equal to 5. So algebraic multiplicity of this lambda 1 is 1 because it is not repeating. It's only it appears only one time. So its algebraic multiplicity is 1. Now this is repeated 2 times. So its algebraic multiplicity is 2. Now the eigenvectors corresponding to lambda 1, we obtain an eigenvector, which is this one, -4, -5, and 2. And corresponding to these two eigenvalues, which are repeated here, we obtain only one eigenvector. We obtain only one eigenvector, which is basically 2, 0, -1. Okay. Its geometric multiplicity is 1. Okay. Its algebraic multiplicity here, algebraic multiplicity, it's 2, whereas its geometric multiplicity here is 1, because we have only one eigenvector. You can find more details about geometric and algebraic multiplicities and their definitions in my lecture slides. I have given you the basic definition. For more details, you can read these things in my notes or as well as in slides, because you have already studied these things in linear algebra course. Now, what to do? How to find K3? The question is how to find, because it is mandatory to find the third eigenvector. Otherwise, we are unable to write the general solution. The general solution must contain 3 parameters, because we have a system of 3 first order differential equation. Solving first equation, we have 1 parameter, constant of integration. Solving second equation, we must have another constant of integration or the parameter. Solving third equation, we must have another parameter. So in total, in the general solution, we must have 3 constant of integration or 3 parameters. But we are unable to write here the general solution because the third eigenvector is unknown. It is basically mandatory to find the third one. Now, how to find it? Let me. कोई बात नहीं. रिकॉर्डिंग रिज्यूम मैंने नहीं की, आई फॉरगॉट इट. तो मुझे पहले याद करवाना था आपने, अब तो हमने काफी ज्यादा कर लिया है. तो
मैंने पूछना था ये t पावर 2-1 और डिवाइडेड बाय 2-1 क्यों किया हमने?
अच्छा, ये basically it's a general formula in order to write the successive eigenvectors or the successive solutions. यहाँ पे देखें, अगर आपके पास ये आपने repeated eigenvalues हैं और eigenvector we can only find one, then the remaining or successive eigenvectors can be computed using this formula. Okay, this is for x1, x2, x3, and so on xp. Okay, if the eigenvalue is repeated p times. तो यहाँ पे देखें किस तरह का फॉर्मूला है. अगर आपने सॉल्यूशन लिखना है फॉर द सेकंड आइगनवेक्टर या इन जनरल pth आइगनवेक्टर, तो p k p pth आइगनवेक्टर आएगा, p पावर p minus 1 divided by p minus 1 factorial e raised power lambda, the eigenvalue which is being repeated. ठीक है, and kp minus 1 power k vector p minus 2 factorial and t power p minus 2 up to so on. यहाँ पे t power 0 आएगा, 0 or 0 factorial which is again 1 by 1. So k factor in p raised by the eigenvalue which is being repeated. So this is what we use in order to find the successive or the subsequent eigenvectors if in the case 2, if we are unable to find the eigenvectors equal to the algebraic multiplicity of that eigenvalue. I hope you got it. हाँ, यहाँ पे let me revise that thing क्योंकि काफी सारा मैंने erase भी कर दिया. We were discussing the case 2 when corresponding to a repeated eigenvalue, if, for example, it is lambda 1, इसकी algebraic multiplicity 1 है, और lambda 2, 3 ये repeated हैं, इसकी algebraic multiplicity 2 है. Now the case 2 which we are discussing, lambda 1 के corresponding k1 आ गया और lambda 2, 3 के corresponding k2 आया. We are able to find only one eigenvector corresponding to these two eigenvalues which are being repeated. Its algebraic multiplicity is 2, and we can only find one eigenvector corresponding to these two eigenvalues, so that its geometric multiplicity is 1. Now, how to find k3? This is the problem which we are going to handle here. Why it is mandatory to find k3? Because I explained you, because we have a 3 by 3 system. We have, let me change the view of that. यहाँ पे ये eigenvalues यहाँ पे repeated हैं, दो, इसकी algebraic multiplicity 2 है, इसके corresponding एक ही eigenvector आ रहा है जो कि हमने find किया. We have to find another eigenvector in order to write the general solution of the given 3 by 3 system. So we must have 3 linearly independent solutions, which forms a fundamental set. So in order to write the general solution, we have to find the third linearly independent solution. So it is mandatory to find k3. How to find k3? I have given you these formulas on the other board, which I have shown you here. These are basically the generalized formula. This is the general formula in order to find the third linearly independent solution. And in this formula, how to find the eigenvectors. Eigenvectors find करने के लिए, I gave you this formula. This basically procedure. This one. First eigenvector, we'll find it in a similar way by using this homogeneous linear system by putting it equal to 0. Second eigenvector के लिए क्या करेंगे? We put here the first eigenvector in order to find the second eigenvector. ठीक है. अगर आपके पास तीसरा eigenvector भी है, means अगर algebraic multiplicity उस root की 3 है, तो you have to find k3 as well. In order to find k3, you have to put k2 here. You'll obtain a non-homogeneous linear system, and then from this system you can find k3 and so on up to k p minus 1. Put it here, and kp you can find the pth eigenvector here. After solving these vectors, you can write the general solutions by using these formulas, and ultimately you can write the general solution of the given linear system. अब यहाँ पे, in order to find k3, what we'll use a minus lambda I, k3 is equal to k2. Sorry. Let me. यहाँ पे, in order to find k3, what we are going to use, those that procedure, a minus lambda I times k3 is equal to k2. We put here k2, and solving this non-homogeneous linear system, which I wrote here, this one. Okay. यहाँ पे k3 है, यहाँ पे हमने k2 put कर दिया because we have already calculated the k2. We have obtained this non-homogeneous linear system. After solving this non-homogeneous linear system, we obtained k3. Now, once we have obtained k3, then in this case, the k2 and k1, sorry, x1 and x2, these two linear independent solutions will be same as we do in the previous case. Now, the third solution would be of this form by using that general formula which I gave you there. So we have three linearly independent solutions, x1, x2, x3, then we can write the general solution of the given system of first order differential equation. I hope you get it. If you have any question, you can ask me. If you have any question, you can ask me. If there is no question, I'm gonna stop till here today.
हमसे imaginary का हमने नहीं करना, imaginary roots का.
We'll do it in the next lecture, inshallah.
So yeah.